So let's look at reciprocal functions. Now, this is a really common question. You might have noticed if you flick through some of the past papers already, the 1 over function x. So the key things to look for. So if the original function's equal to 0, then when I turn it upside down, then it must become undefined, because you can't go 1 divided by 0. So we'll end up with a vertical asymptote. Here's random function. And I thought I'd pick a random function here, which has got pretty much everything I could think of. It's got a vertical asymptote, it's got turning points, it's got horizontal asymptotes. So let's see how we go. So each one of these x-intercepts will become vertical asymptotes. So right, we know we've got vertical asymptotes there. Now what else? If we think about what happens out at infinity then, well, out at infinity, yes, you can't actually turn infinity upside down, but we think of 1 over infinity as 0. Because if you're going to turn the biggest possible thing you can imagine upside down, you must end up with the smallest possible thing, which is 0. So in other words, they become x-intercepts, sort of. Now what I mean by sort of, it didn't exist in the original graph, so it can't exist in the new graph. So what we'll end up with is a point discontinuity there. Say I had to draw the reciprocal of 1 over x. Okay? So in the original graph, x equals 0 didn't exist. So when I turn it upside down, well, if I was to turn 1 over x upside down, you'd get y equals x. But I can't substitute 0 into this function, because I'm not substituting into y equals x. I'm substituting into 1 over x. So we end up with a point discontinuity at the origin. So it's like we saw yesterday. If it didn't exist in the original curve, it can't exist in the new curve, because we still can't substitute it in. So on random graph here, I end up with a point discontinuity at the only x-intercept we'll have, isn't it? We've only got one vertical asymptote. Okay. Now, remember yesterday I said for these graphs, 1 becomes a key point. Because if you turn 1 upside down, you get 1. So if we can locate where the y value of 1 is, that's great, because we know that point will stay on the original curve. Similar with negative 1. You turn negative 1 upside down, you're going to get negative 1. There we go. Yeah, pretend that's a negative 1, okay? It was meant to go to negative 1. But negative 1's there. Okay. Now, let's have a look at my horizontal asymptote. My horizontal asymptote is less than 1. So if I turn it upside down, it's going to become bigger than 1. I suppose I could get a ruler and work out exactly what the scale is, but I'm just doing a rough sketch, so I'm going to say, okay, well, it's above. Now, when we find reciprocals, if the original curve is increasing, the reciprocal will be decreasing, and vice versa. So we know whenever the original curve is going up, our new curve will be going down. The sign's not going to change. I mean, turn a positive number upside down, it's going to stay positive. So let's try and piece that together. For us to work out then where this graph is travelling, and have a look at what I've done. And what I'm basically doing is locating again at 1, and I'm saying, hey, over here the original graph is below 1, but above the asymptote. So when I turn it upside down, it'll be below the asymptote and above 1. So I know it'll be in there somewhere. Next section is above 1 completely. So it'll go below 1, but it can't become negative, because a positive will stay positive. Then here, we've got below negative 1, so it goes above negative 1. Next section is between naught, so above negative 1, so it goes below negative 1. Next section is the original graph is below positive 1 and cutting the horizontal asymptote. So this one will go past the horizontal asymptote, and so on and so on. And I make that decision for each of those bits. I suppose we could get the y-intercept Well, the way I've drawn mine, I wonder if I did on my new curve, we'll see in a sec. But I've got the original graph going through the new horizontal asymptote. I suppose that means the new graph should go through the old one. We could use calculus. The derivative of 1 on function x would be minus the derivative on the function squared. So that tells me that on the original graph where we have stationary points, my new graph will also be a stationary point, because f dash x is equal to 0. So when I substitute it into the new derivative, I still get 0. So stationary points will remain stationary points. The y value might change, but on that x value there'll still be a stationary point. Whee, there we go. There's our new graph. So the stationary point remained. Let's just get rid of the shading and everything. Oh, there we go. What a lovely graph. Y equals 1 on function x. Okay, so that's reciprocal graphs.